In this video, we are going to learn the concept of arrival cycles in ProModel, and we are going to learn how this feature is going to help us to capture more complexities in simulation models that we develop. So to be able to get a better understanding of what do we mean by arrival cycles, let's look at one example. In this example, we are going to model a burger shop. So in this burger shop, customers arrive to the system and they go to incoming. From there, they go to server queue. And after standing in the queue, they go to the server to request for a table and pick their food. And then from there, they go to one of these 6 dining tables available to eat their food, and then they leave the system. Okay. So these 6 dining tables are parallel locations. So for the incoming area, we consider capacity of infinity, no queuing rule. For server queue, we again consider capacity of infinity, first in, first come rule. But then everything else will have capacity of 1. The server and each one of these dining tables will have capacity of 1. So there are a couple of things that we know about this problem statement. The number of customers that this burger shop gets in every 24 hours has a normal distribution, average 100, and a standard deviation 5. Okay, so these are total number of customers that come to the restaurant in every 24 hours. The time that the customers spend with the server to place their orders and so forth has a uniform distribution, average 5, half fit 2, and the time that they spend at dining tables to eat their food has normal distribution, average 15, and a standard deviation 3. There is one more piece of information that we know about this problem. These number of customers that we receive a day or in every 24 hours, the number of customers that come to this burger shop, yes, follows this distribution. On average, 100 customers come to the burger shop. These number of customers are spread throughout the day, like a real world, right? It's not that all these 100 customers arrive at one point. Their arrival times are spread throughout the day. And that's another piece of information that we know. So from this burger shop works from 6 a.m. all the way to 9 p.m. Using some data, we know that number of customers that come to the system between 6 a.m. to 6:30 a.m. is 5%. And then between 6:30 a.m. to 8 a.m. is 20%. Between 8 to 11, 5%. 11 to 1 p.m., 35%, and so forth, all the way to the last hours of the day from 7 p.m. to 9 p.m., that's again 5%. So as you can see, the sum of these percentages add up to 1. So that tells us that these 100 people, or most 100 people, this tells us that these 100 people on average that are coming to this burger shop each day or in every 24 hours is spread throughout the day based on these percentages, okay? So we want to see how we can capture that in ProModel, because in ProModel, if I let the customers to come to the system in a batch, all of them arrive at one point. They come in a batch and all of them arrive in one point. However, I don't want that to be the case here. This is the total number of customers that I know I'm going to get in a day. However, these number of people are going to arrive over time. And I wanted to be able to capture this complexity in ProModel. The arrival cycles feature of ProModel enable us to be able to do that. So let's go back to the model. I want you guys to create a model. It's called Newport Burger Arrival Cycles. Please create a new model, name it as Newport Burger Arrival Cycles. Create these locations for incoming, server queue, server, and then 6 parallel locations for the dining tables or the dining. The entity that we are going to define is going to be customers. Customers are the ones that are going to come to these restaurants, to this burger shop. And then for the arrival, let's see what we have. So for the arrival, based on the information that we had here, in every 24 hours, the burger shop gets about, on average, 100 customers. So the customers come to the incoming, and these customers come in every 24 hours. So this is the number of customers that we get in every 24 hours. So that's our inter-arrival time, right? Or that's our frequency. So our frequency is going to be 24 hours. And then I need to take care of the fact that we get about this number of customers a day. So that's going to be my quantity each. So the number of customers that come to the system in each arrival is going to come from this distribution, normal distribution, average 100 and standard deviation 5. Okay. And these customers can come to the system from the start of the simulation, and the occurrence is 100. And given the fact that the frequency is 24-hour, occurrence of 100 means that I want to run this simulation only for 100 days. The inter-arrival is 24 hours. So in each 24-hour, a group of customers come in, and I want to continue this till I get 100 group of customers. And given that these groups come to the system in every 24 hours, that's equivalent to running the simulation for 100 days. Okay. So as we all know, if I just leave the arrival as is, in every 24-hour, simulation will create a batch that are going to come to the system. At the start of each 24 hours, I'm going to get about on average 100 customers. They're going to come to the system. They are going to go through the process one by one, but that's how the simulation is going to implement this. In every 24 hours, at the start of every 24 hours, I'm going to get this number of customers, and this is going to continue for 100 days. However, as we talked, we don't want that to be the case. I want the number of customers that come to the burger shop to spread across these 24 hours, to spread across the day. So this is how this is going to spread from 6 a.m. to 9 p.m. And from 9 p.m. all the way to 6 a.m. next day, 0% customers come to the system. To be able to let ProModel to incorporate this complexity into the picture, what I need to do is to define arrival cycles. Arrival cycles can be defined using this feature here, see, in the menu, arrival cycles. So if I click on the arrival cycles, here I can define the name of the arrival cycles. So here I can say the name is going to be burger arrival, or any name that you like. So when you press enter, here, the rest of the row is completed automatically. Percentage, if you click on the column, it has the percentage or the quantity. Percentage means how are you going to tell me how these people are spread throughout the day, for example. So here, what I have is the percentage of people across the day. If I had number of people to just say, okay, of these 100 people, for example, 3 of them come between 6 to 6:30 a.m., 18 of them come between 6:30 to 8 a.m. If these numbers here would represent how many of those 100 people come at which time interval, then here I would use, instead of percentage, I would use quantity. However, that's not the case here. The numbers that we have here tells us the percentage of numbers, the percentage of that 100 people on average that come to the system, that come between 6 to 6:30 a.m. and so forth. So I'm going to pick percentage here. I'll talk about accumulate in a little bit. So for the table, I'm going to double click on the table, and then this tab is going to open, okay? So this is the place where I can enter the information related to that table, where I know what percentage of people come in which time interval of the day. So what I have here is that in the first half an hour of the simulation, 5% coming. And then in the next an hour and a half, 20% coming. So this is from time 0 in the simulation till time 0.5, okay? And then from time 0.5 till time 2. So if 6 a.m. is the start of the simulation, when the simulation time is 0, at 8 a.m., 2 hours into the simulation or 2 hours into the day, the simulation clock will be 2, okay? And the next row is where the simulation time is going to go from 2 to 5. So this is 11 a.m., 5 hours after 6 a.m. So the simulation time is 5. So going from hour 2 to hour 5, then I have 5% of those number of people to enter the system. Okay. So the way to enter that in ProModel is that to say that, okay, for the first half an hour, so here I'm just going to put this as 0.7. And here 5%. So this has the percent. We don't need to do anything. 5% of the people to come to the system in the first half an hour. Then in the next an hour and a half till I get to hour 2 in the simulation, 20% of people would come in. So then from hour 0.5 till hour 2, 20% are going to come in. Then from hour 2 till hour 5 in the simulation, 11 a.m. it would be equivalent to hour 5 in the simulation. So then from hour 2 to hour 5, 5% will come to the system. So from hour 2 to hour 5, 5% of those people will come to the system. And then from 11 to 1, that's going to be from hour 5 to hour 7, 35%. And then from hour 7 to hour 11, 10%. And then from hour 11 to hour 13, 20%. And from hour 13 to hour 15, 5%. Okay. So from hour 11 to hour 13, 20%. And from hour 13 to hour 15 of the simulation, 5%. That is how we have to enter the information related to this table in an arrival cycle. So the first row says that from time 0 to time 0.5, 5%. From time 0.5 to hour 2, 20%. And then from hour 2 to hour 5, 5%, and so forth. That's how this table is going to be read. And the time that we put here, they're in hours, as you can see here. And if you remember, I told you, I'm going to tell you in a little bit what is the meaning of cumulative column. So here, the way that I put these percentages are not cumulative, and that's why the cumulative is no. However, you have the possibility to pick the cumulative as yes. If you pick the cumulative as yes, then for these percentages, you also have to put them as cumulative. If I put the cumulative as yes, then here I would say for between hour 0 to 0.5, 5%, and then between hour 0.5 to 2, 25%. So I put the percentages in a cumulative format. And then from hour 2 to hour 5, I'm going to have 30%. So that 25% plus 5% is 30%. The simulation would know that these are cumulative percentages. So it does the corresponding deduction to find out what is the exact percentage associated with this time interval. But these values that we put here are going to be treated as cumulative probabilities if I pick the cumulative to be yes. So that's how we can identify the arrival cycle. Okay. Make sure to save. Now let's go back to the arrival. So here, as we talked already about it, all that simulation is going to do is that in every 24 hours, right at the start of every 24 hours, is going to let about 100 customers to come to the system together. However, we know that that's not what we want. We want to spread these 100 customers on average in these 24 hours. So the way to do it is to click on quantity each. And here you see arrival cycles. Now this burger arrival that we define as the arrival cycle is listed here. So pick this burger arrival, which is our arrival cycle, and then press OK. So then in the quantity each, this would be the total number of people that I'm going to get in every 24 hours. And then the burger arrival, this is my arrival cycle that is going to be used so that this number of people that are going to come to the system in every 24 hours are not just going to arrive at the start of the 24 hour, all of them together, but they are going to spread across these 24 hours. And also I want you guys to pay attention. We said here the frequency is 24 hours. In every 24 hours, this number of customers come to the system. So if I do not put the unit of time right next to 24 hour, that means the default unit of time in the model is in hours. Okay, so in this model, it just happens that I have chosen the default unit of time to be hours. So I press OK. I also want you guys to pay attention that here next to 24, I did not put hour as the unit of time. So here is our inter-arrival time. In every 24 hours, we receive this number of customers, right? So if I do not put hour next to 24, that means the default unit of time in this model is hour, as you can see here. It just happens that I just chose hours to be the default unit of time in this system, but you don't have to do that. So you can keep the unit of time as minute if you want, then write the inter-arrival time in terms of the minutes, okay? But I decided to pick the unit of time as hours, and then here I'm just going to enter 24, and I don't need to worry about putting the unit of time here. Next in processing, I'm going to pick the customer, and then customer that is already at incoming goes to the server queue, from server queue to server, from server to dining, and finally from dining to exit. The time that they spend with the server to place the orders and so forth has uniform distribution, average 5, half it 2, and the time that they spend at the dining table to eat their food has normal distribution, average 15, and standard deviation 3. So we are now ready to run the simulation. Make sure to save your model before you proceed, guys. And I want you to pay attention to the fact that since default unit of time in the system is in hour, if these processing times are in minute, I want to put them next to these processing times, okay? So if these process times are in minutes, so do not forget to put the minute next to them because the default unit of time is in hour, okay? So now we are ready to run the simulation. However, before we do that, I want you guys to ask yourself if we need to specify the simulation runtime in this model. The answer is no, because if you remember from the arrival, the occurrence is 100. The inter-arrival time is 24 hours. And each 24 hours obviously represents a day. And we are going to repeat that only 100 times. So this is equivalent to running the simulation for 100 days. And the simulation is going to just continue till all these arrivals happen. And when everyone in the system gets the service and leave, the simulation stops automatically. So we do not need to specify a simulation runtime. So this is what I have. In that 100 days, about 10,000 customers have received the service and have left. And makes sense because if you remember, in each day we get on average about 100 customers, and I'm simulating the system for 100 days. So 100 multiplied by 100 is on about 10,000, and that's the total exit that we see here. And on average, each person spends in the system about 0.6 hours to finally get the service and leaves. And right here, we can see the percentage in operation of the dining tables. So since the allocation rule for these dining tables was first available, so the customers went to the first one that is available. If that one is busy, then to the second one, then to the third one, and so forth. As you can see here in the rest of the dining tables, the percentage in operation is less and less. And finally, the last one shows the average of the percentage in operation in all dining tables. So basically, the concept of arrival cycle enable us to capture the possibility that these group of customers that I know I'm going to get in a day, I know the total number of customers that I'm going to get in a day. However, these number of customers are spread throughout the day. The concept of arrival cycles enabled us to capture that. The arrival cycle feature in ProModel enables us to identify how the customers are spread throughout the day. And we can identify that through percentages or the quantity. And as long as we know how people are spread throughout the day.